Welcome, curious minds. Have you ever looked up at the night sky and wondered if our sun has a sibling out there? Maybe a long-lost twin.
It might sound a bit like science fiction, yeah.
Right. But astronomers have actually been on this, cosmic detective hunt for just that. Stellar twin binaries.
hmm
These are star systems where the two stars are, well, surprisingly, almost impossibly alike in mass. So today, we're taking a deep dive into this really fascinating phenomenon.
And our mission today really is to unpack the incredible journey of discovery around these stellar twins, especially how the groundbreaking Gaia mission has finally confirmed they're, well, pretty widespread.
Okay.
Then we'll dig into the leading theories on how they actually form, and in a truly surprising twist, what their presence or maybe even their absence might tell us about the earliest days of our very own solar system.
Sounds great. We've got a stack of sources guiding us here from, foundational studies going back to the 1970s all the way up to really cutting-edge research using the latest data.
Yep, lots to cover.
Okay, so let's start at the beginning. When astronomers talk about twin binaries, what exactly are we referring to? It sounds like it's more than just any two stars orbiting each other.
Yeah, you're right to point that out. It's not just any binary. We're talking about a very specific kind of binary system where both stars are, well, nearly equal in brightness.
Okay,
And because brightness and mass are linked, that means they're also nearly equal in mass.
right.
Astronomers quantify this with something called the mass ratio, Q.
Q.
Yeah, simple division. The mass of the secondary star divided by the primary star's mass, m2 over m1.
Got it.
For twins, Q is very, very close to 1.0, like 0.95 or higher.
Almost identical.
Exactly. And this isn't just, a neat number. It actually challenges some of our long-held ideas about how stars form. It suggests a very specific, almost like predestined connection between these stellar siblings.
Okay, so this idea of, perfectly matched stellar twins. It isn't a brand new concept then. Astronomers have been seeing hints of these for a while, kind of scratching their heads.
Oh, yeah, indeed. The idea has quite a rich history, actually. It goes back decades. As early as 1974, an astronomer named Virginia Tremble looked at over 800 binary systems.
Wow, 800.
Yeah, a lot for the time. And what she found was that the distribution of these mass ratios, the Q values, was bimodal.
Well, bimodal meaning...
Meaning it had two distinct peaks, like two humps on a graph. One peak was for pairs, where one star was much less massive, maybe Q around 0.3 or so.
Okay, the unequal pairs.
Right. But then there was this surprising second peak, pretty much precisely at Q equals 1.0.
Ah, the twins.
Exactly, suggesting a whole population of these equal mass components.
Interesting. And then didn't Lucy and Rico build on that, refine the observation?
Precisely. In 1979, Lucy and Rico, they looked at a smaller sample, about 178 systems, but maybe with better data for those specific ones. And they identified a really precise narrow peak for these nearly identical twins, right around a mass ratio of 0.97.
Big, even narrower.
Yeah, and what's really fascinating here is that they didn't just note the peak. They attributed it directly to an underlying formation mechanism. They were already thinking, how do these things get made?
Right, not just chance.
Not just chance. They considered a theory called fission, where a really rapidly spinning young star, a protostar, basically breaks apart.
Okay.
But they dismissed it because the simulations, even back then, showed fission tends to produce binaries with much lower mass ratios, like around 0.2, not twins.
Ah, so that didn't fit.
Didn't fit.
Yeah.
So instead, they favored something called fragmentation of the collapsing cloud structure that forms the star. Although, truth be told, later models kind of moved away from that specific fragmentation idea, too.
So these early findings just sort of deepened the cosmic mystery then. What was the next big step in trying to figure this out?
Well, the mystery definitely deepened, yeah. Then, fast forward to 2000, Andrei Tokovinin revisited the distribution. He looked at about 100 systems called double-lined spectroscopic binaries.
Double-lined. What's special about those?
It means we can actually see the spectral lines, the light signatures from both stars distinctly in the telescope data.
Ah,
Yeah.
okay. So you get info on both stars individually.
Exactly, which gives you a much more accurate picture of their individual properties, like their masses and velocities. It helps reduce certain observational biases you might get if one star drowns out the other.
Makes sense.
So Tokovinin confirmed that solar-type binaries, stars like our sun, specifically those with relatively tight, fast orbits, shorter than about 40 days period.
Okay, the close ones.
Yeah, the close ones. They showed a statistically significant excess of systems with mass ratios greater than 0.95. He was actually the one who officially called these twins.
Ah, so he coined the term. Did his work offer any clues about how they formed?
He certainly had a compelling idea. He noticed, like others before him, that this twin population seemed to be absent, or at least much less common, in wider binaries with longer
Right,
periods.
the under 40-day thing.
Exactly. So Tocqueville favored a formation scenario where these close orbiting twins started out maybe a bit wider, but then evolved to become relatively close, perhaps through, dynamic interactions within their chaotic birth clusters.
Busy neighborhoods.
Very busy. And then crucially, subsequent accretion of gas and dust while they were still wrapped in this massive envelope of material. Basically, they got closer and then bulked up together.
Interesting.
He even pointed out that quite a few twins seem to have a third star orbiting the pair, a tertiary component.
Oh, wow.
Yeah, and he saw that as kind of circumstantial evidence for this more dynamic formation mechanism involving interactions.
So the evidence wasn't just from spectroscopy, right? You mentioned other clues earlier.
Absolutely. Totally independent of that spectroscopic data, just the sheer frequency of nearly equal component binary stars was also used to explain something astronomers see in star clusters. It's called the binary sequence.
Binary sequence. Okay, what's that?
Well, astronomers use these charts called color magnitude diagrams, basically plotting a star's brightness against its color or temperature.
Right, the Hertzsprung-Russell diagram, that sort of thing.
Exactly that kind of plot. Single stars typically fall along a nice, well-defined line called the main sequence.
Okay.
But if you have a binary system where both stars are nearly identical in mass and brightness, and your telescope sees them as one point of light,
It looks brighter than a single star of that color.
precisely, you're seeing the light from two stars bundled together. So these twins appear on a separate sequence on the diagram, running parallel to the main sequence, but brighter, about 0.75 magnitudes brighter, typically.
Now they saw this.
Oh, yeah. It's a really clear feature in well-studied open clusters like Praesepe, the Beehive cluster, and the Pleiades. A clear sign that nearly equal mass binaries are common, at least in those clusters.
So all these early hints were really intriguing, but it sounds like for a long time actually studying these systems properly was tricky. Maybe observational biases, selection effects, that kind of thing.
That's exactly it. You might preferentially find brighter pairs or pairs at certain separations just because of how telescopes work or how surveys are designed. It made it hard to be sure if the twin peak was truly real or just an artifact.
Okay, so here's where it gets really interesting. How did a massive mission like Gaia just completely change the game, cut through all that noise?
Gaia it was a monumental leap. It provided just a huge advance in statistical weight, as the researchers put it.
Statistical weight meaning just way more data.
Orders of magnitude more data. Those early studies might have used a few hundred systems, maybe 1,000 if they were lucky. Gaia gave us data on millions of stars with incredible precision.
Wow.
So, El-Badri and colleagues, in a key study in 2019, used data from Gaia's early data release 3, EDR3. They defined a sample of 42,000 wide main sequence binaries. Just think about that number compared to 800.
Yeah, it's enormous.
And this massive data set allowed them to unambiguously, no question about it, identify a sharp, statistically significant excess of equal mass twins.
And not just close ones.
No. That was another key finding. This twin excess extended out to truly vast separations. We're talking 1,000 to even 10,000 astronomical units AU.
10,000 AU.
Yeah.
That's huge. Remind us, an AU is Earth-Sun distance.
Yep, about 93 million miles or 150 million kilometers. So 10,000 times that. These are incredibly wide pairs, way beyond the size of our solar system.
And the peak was still there. Still sharp.
Still there, still very sharp. A steep increase in the number of pairs right between mass ratios of 0.95 and 1.0.
That's staggering.
Yeah.
What did that just sheer amount of data allow them to see that wasn't clear before? Did it resolve old debates?
Absolutely. So in a follow-up paper in 2021, the same team used an even larger sample. Get this, 1.26 million resolved binaries within about 3,300 light years.
A million. Okay, that's just mind-boggling.
It really is. And their data just beautifully showed this clear excess of systems where the magnitude difference, the brightness difference between the two stars was near zero, just confirming the equal brightness, equal mass phenomenon beyond any doubt. And this statistical power, the sheer number of stars, was crucial. It allowed them to definitively confirm that the twin phenomenon is not just some observational bias or a selection effect, as some folks had worried about for decades.
So it's real.
It's real. And moreover, remember Tocqueville's idea that the twin population kind of fell off for longer periods beyond that 40-day mark?
Yeah.
Well, the newer, Much more comprehensive Gaia data did not confirm that cutoff. It seems twins exist across a much wider range of orbital periods and separations than previously thought.
Wow. So Gaia basically rewrote the book on twin frequency and distribution.
Pretty much, it provided that unambiguous confirmation.
Okay, so with Gaia's powerful confirmation settling the if, the big question really shifts from if these twins exist to how they actually came to be, right?
Exactly. The focus moves squarely onto formation mechanisms.
And you mentioned earlier that how they form might depend on how far apart they are. Do these perfectly matched pairs form differently depending on their separation?
That seems to be the leading idea, yes. The formation mechanisms likely vary with the separation of the two stars.
Okay, so let's break that down. What about the really close pairs? Like orbiting each other very quickly?
Right, for the very smallest separations, maybe inside, say, 10 AU or so, a leading theory involves formation through accretion within what are called circumbinary disks.
Circumbinary, meaning around both stars.
Exactly. Imagine a single large disk of gas and dust swirling around both stars as they orbit each other.
Okay, I can picture that.
Well, theoretical models and simulations show that the lowest energy state, the most stable configuration for a binary system embedded in such a disk, corresponds to having equal mass stars.
Huh. Why equal mass?
It's about how gravity and gas dynamics interact. Essentially, the system settles into a state where the gravitational torques from the disk and the stars balance out most efficiently when the masses are equal. The models also predict they'll end up on nearly circular orbits, with their spins synchronized and aligned with the orbit of the disk itself.
Wow, so the physics of the disk naturally pushes them towards being twins.
That's the idea for the close ones, yeah. It's a really elegant explanation for why they'd prefer to be so perfectly matched and aligned.
Okay, so that covers the really tight pairs. What about those wider pairs then? Maybe out to a few hundred AU.
Yeah, for those wider separations, let's say up to maybe 100 or 200 AU, which is still within the realm of plausible disk sizes, a process called competitive accretion within that circumbinary disk seems like a good candidate, though maybe not a total consensus yet.
Competitive accretion. Sounds like they're fighting over food.
Kind of. In this scenario, remember the secondary star, the initially less massive one, actually orbits further out from the system center of mass than the primary star does.
Right, because the center of mass is closer to the heavier star.
Exactly. So the secondary star effectively sweeps through a larger volume of the disk as it orbits.
Ah, so it encounters more gas and dust.
Precisely. It gets a better chance to accrete, to gobble up more material from the disk compared to the primary star. And this process naturally drives the mass ratio towards 1.
So the smaller star gets a better shot at catching up.
That's the essence of it. It helps equalize the masses over time as they both feed from the surrounding disk.
Okay, that makes sense for intermediate separations. But what about those really wide twins Gaia found? Hundreds or even thousands of AU apart. That's way bigger than these disks usually are, right?
That's the key question. For separations greater than, say, 100 to 200 AU, you're right, that's generally beyond the typical maximum sizes of observed protoplanetary or circumbinary gas disks.
So competitive accretion wouldn't work out there.
Probably not directly, no. So the most plausible scenario for these very wide twins is that they didn't form that far apart.
Ah, they formed closer in.
Exactly. They likely formed initially at much closer separations, maybe through those circumbinary disk accretion mechanisms we just talked about, becoming twins early on.
And then something happened.
And then their orbits were subsequently widened, stretched out by dynamic interaction.
Like what kind of interactions?
Things happening within their crowded birth clusters, encounters with other stars maybe passing through dense gas clumps. These gravitational nudges and kicks over time could separate the pairs significantly without necessarily disrupting the fact that they're twins.
So they're born twins, but then get flung further apart.
That's the leading hypothesis for the widest pairs. And we might get more clues by studying the alignment of their spin axes, the direction they're rotating.
How would that help?
Well, if they form together in a circumbinary disk, their spins should be relatively well aligned with each other and with their orbit. If they were just random stars captured together or heavily perturbed, you might expect less alignment. So, comparing the spin alignment of wide twins to other wide binaries could give us hints about their origin story.
Okay, so this idea that wide twins formed close and then got widened, that sounds like a pretty dramatic journey. How would scientists even find evidence for that kind of history, especially for stars that are so far apart now?
Yeah, that's a critical point. How do you prove they started closer? Well, a really interesting recent development came from Huang and colleagues in 2022. They looked at the eccentricity of the orbits of these wide twins.
Eccentricity,
Yeah.
meaning how stretched out, how elliptical their orbits are.
Exactly. A circular orbit has an eccentricity of 0. A very stretched out ellipse is close to 1. And they found something truly remarkable.
What did they find?
They inferred that essentially all the wide twins they studied must be on extremely eccentric orbits.
Extremely eccentric, like how extreme?
For the twin population they looked at, between about 400 and 1,000 AU separation, they inferred eccentricities almost exclusively in the range of 0.95 to 1.
Wow, 0.95 to 1. That's practically a straight line dive towards the center.
Almost. It means that while their average separation, their semi-major axis, is really wide.
Hundreds of AU.
Right. Their closest approach, what astronomers call the pericenter distance, is actually incredibly small. Only about 10 AU, maybe 20 AU at most for many of them.
Only 10 AU? That's like Saturn's distance from the sun.
Exactly. So they spend most of their time incredibly far apart, but they have these brief, relatively close encounters.
And what does that imply about their history?
Well, it's highly consistent with that scenario we just discussed. Twins are born close together, maybe in those circumbinary disks where they equalize their mass.
Right.
And then their orbits get massively stretched and widened by subsequent dynamical interactions. Think of it like a gravitational slingshot effect.
Okay.
These interactions tend to pump up the eccentricity while also increasing the average separation. So finding these incredibly high eccentricities is strong evidence that they didn't form way out there, but rather started close and got dynamically excited.
What kind of interactions could do that? Still stuff in the birth cluster.
It could be things in the birth cluster, yeah. Encounters with other stars. But it could also be forces acting later, like tidal forces from the entire Milky Way galaxy's disk pulling on them over billions of years. Or maybe scattering events from passing giant molecular clouds or even other field stars after they've left their birthplace.
So multiple ways to stretch them out after they form as twins.
Yes, we're playing, yeah.
Okay, wow. This has been a wild ride through the lives of binary stars, formation, dynamics. But let's try and bring it back home. What's the biggest, maybe most surprising aha moment here? How does all this potentially connect back to us, to our very own sun?
Okay, yeah, this is where it gets truly exciting and maybe a bit speculative, but grounded in these findings.
Ready?
It might seem like a totally unrelated topic, but astronomers have been grappling with two big puzzles in our own solar system for a while now.
Okay, what are they?
First, there's the mystery of the origin of the outer Oort Cloud.
The Oort Cloud. That's
Yeah.
that huge distant shell of icy comets way, way out past Neptune, right?
Yeah, exactly. Tens of thousands of AU away. We know it's there. But explaining how all those icy bodies got out there and formed that specific structure is actually quite tricky with just the sun and the known planets.
Okay, puzzle number one. What's number two?
Puzzle number two is the curious clustering of the orbits of some of the most distant objects we have found beyond Neptune, these extreme trans-Neptunian objects, or ETNOs.
This is the whole Planet 9 thing.
Precisely. The way their orbits seem to be aligned has led many astronomers to hypothesize that there's a massive unseen planet, Planet 9, lurking way out there, maybe around 500 AU or so, gravitationally shepherding these smaller bodies.
Right. Still looking for that one.
Still looking. So you have these two big puzzles, the Oort Cloud structure and the potential existence and origin of Planet 9.
Okay. So how on Earth do twin binaries fit into this picture here in our solar system?
Well, in 2020, two astronomers, Amir Siraj and Avi Loeb, proposed a really provocative idea. It directly connects the prevalence of stellar twins to these solar system mysteries. They ran simulations and showed that if our sun had an equal mass companion, a twin, way back when the sun was forming in its birth cluster.
Our sun had a twin.
Temporarily, that's the key. If it had a temporary twin, maybe orbiting at a separation of around 1,000 AU, just while they were still in that crowded birth cluster,
Okay.
that binary configuration would have been much more effective at capturing objects than a single star like our sun would be on its own.
More effective at capturing what?
Capturing icy bodies from the surrounding cluster environment to form the Oort Cloud, and potentially capturing a free-floating planet from the cluster that could have become Planet 9.
Whoa, hold on. Our sun had a twin, and it helped grab comets and maybe Planet 9.
Yeah.
But wouldn't we have noticed a twin star? I mean, 1,000 AU is far, but not that far astronomically.
That's a great question, and you're right. Previous ideas about a current close companion to the sun, like the old nemesis hypothesis, have been pretty definitively ruled out by observations. We just don't see one nearby now. But the beauty of the Siraj and Loeb model is that it posits this twin companion only existed while the sun was in its birth cluster.
And then what happened to it?
It got ejected. The birth clusters of stars are chaotic places. Gravitational interactions are frequent. So the idea is that the sun was born as part of a wide twin binary. This configuration helped capture the Oort Cloud objects and potentially Planet 9 through complex three-body interactions.
Okay.
And then before the cluster dispersed, another star likely passed too close, disrupting the binary and flinging the sun's twin out into the galaxy, leaving our sun effectively single.
So the twin did his job shaping the outer solar system and then got kicked out.
That's the provocative hypothesis. It relies on the fact shown in simulations that binaries are way better gravitational nets for capturing stuff than single stars are.
That's incredible. So these distant observations about how common twin stars are, especially wide ones, might actually point to a long-lost sibling of our sun, a cosmic partner that helped sculpt our own planetary neighborhood before vanishing.
Exactly. It connects the galactic prevalence of twins, confirmed by Gaia, to the specific architecture of our own solar system's outermost regions.
And is there any way to test this, besides finding Planet 9 itself?
Well, yes. One of the really exciting parts is that this temporary twin scenario makes predictions. It predicts there should be an overabundance of captured dwarf planets out there, with orbits similar to the proposed Planet 9, maybe even more than you'd expect if Planet 9 was formed in place or captured by the sun alone.
Ah, so finding more objects like Sedna or the other ETNOs.
Yes, and potentially finding a whole population of them. And the best part, these predicted objects, these potential fossil clues to our sun's past life as a twin, could soon be discoverable. New powerful survey telescopes like the Vera Rubin Observatory are coming online soon, and they're designed to find exactly these kinds of faint, distant objects.
Wow. So we might actually find the gravitational echoes, the leftover crumbs, from our sun's lost sibling.
It's a definite possibility, imagine that.
What an absolutely incredible journey we've taken today. Seriously. From just those first tentative hints of equally matched stars decades ago.
Yeah, those bimodal distributions.
Right, to Gaia's stunning, definitive confirmation that twins are real and widespread, even at huge separations, and then to connect it all the way back here to this breathtaking possibility that our very own sun might have started life as part of a cosmic pair that shaped our home.
It really does reshape how you think about our place, doesn't it?
It completely does.
And if you think about the bigger picture, the very existence and the strange dynamics of these twin binaries, especially the wide eccentric ones, it really suggests that the early lives of stars, including our sun, were probably far more dynamic, more chaotic, maybe more interactive than we often picture.
Less serene nursery, more demolition derby.
Something like that. And it raises this really important question, I think. If the very architecture of our outer solar system, the Oort Cloud, maybe even Planet 9, might be subtly shaped by a long-lost sibling star, what other missing links are out there? What other subtle clues in planetary systems or star populations are waiting for astronomers to connect the dots back to their turbulent beginnings?
That's a fantastic question to ponder. So the next time you look up at the night sky, maybe don't just see single points of light. Consider the hidden partnerships, the gravitational dances, the dramatic breakups that might have sculpted them and maybe even sculpted us in a way.
Yeah, it adds another layer to the cosmic story.
Absolutely. We really hope this deep dive has given you, our listeners, a whole new perspective on the stars above. Thanks for joining us.